In the vast universe, there are incredible events happening that are beyond our wildest imaginations. These celestial phenomena, from massive asteroid collisions to distant spacecraft journeys, unfold on a scale that dwarfs anything we know on Earth. Join us on a fascinating journey through time and space as we delve into the cosmic events you will miss. The thought of an asteroid collision with Earth is enough to send shivers down anyone's spine, and the asteroid known as Apophis has certainly captured public imagination. Apophis, named after the Egyptian god of chaos, is a near-Earth object that was discovered in 2004. Approximately 340 meters in diameter, this massive rock has a potential energy equivalent to over 800 megatons of TNT. For context, that's more than 15 times the explosive force of the most powerful nuclear bomb ever detonated. If Apophis were to collide with Earth, the effects would be catastrophic, although not globally apocalyptic. The immediate impact zone, likely spanning several hundred kilometers, would experience immense devastation, flattening buildings, vaporizing surroundings, and creating a massive crater. The shockwave alone could level cities and forests far beyond the initial impact site. This would be accompanied by a seismic shock, triggering earthquakes that could be felt thousands of kilometers away. The collision would also eject massive amounts of dust and debris into the atmosphere, potentially leading to what scientists call an impact winter. The sun's light could be significantly blocked for months, causing global temperatures to plummet, disrupting agriculture, and bringing about a period of worldwide famine. Voyager 1, the farthest human-made object from Earth, embarked on its historic journey in 1977. It has since traversed past the outer planets and entered interstellar space, which it did in 2012. This spacecraft is moving at a staggering speed of over 38,000 miles per hour, but despite its velocity, interstellar distances are so vast that it will take quite some time before it encounters another star. In approximately 40,000 years, Voyager 1 is predicted to pass within 1.5 light-years of a star called Gliese 445. Situated in the constellation Camelopardalis, Gliese 445 is a relatively dim and cool red dwarf. While this might sound thrilling, Voyager 1's journey through space is more about what it represents than what it will practically achieve in terms of close encounters. Over the millennia, it will pass through the sparse and largely empty realm of interstellar space, facing an environment filled primarily with low-density gas, cosmic rays, and magnetic fields from the galaxy. The particle density and radiation levels are much lower than those of the solar system, meaning Voyager 1 will continue its lonely voyage, sending back data for as long as its power source permits, offering humanity a rare glimpse into the outer reaches of our celestial neighborhood. The phenomenon known as geomagnetic reversal, where Earth's magnetic field flips, has intrigued scientists for centuries. These reversals are not instantaneous, but occur over thousands to millions of years. The last reversal, known as the Brunhes-Matuyama reversal, happened approximately 780,000 years ago. When Earth's magnetic field undergoes this flip, the magnetic north and south poles swap places. During the process of a geomagnetic reversal, Earth's magnetic field weakens, sometimes to as low as 10% of its usual strength. This weakening can have numerous effects on both the planet and life itself. One of the primary concerns is the increased exposure to cosmic rays and solar radiation, which can reach Earth's surface with greater intensity due to the weakened shield. This could have implications for living organisms, particularly affecting those that rely on Earth's magnetic field for navigation, such as migratory birds, marine turtles, and even certain bacteria. Furthermore, the increased radiation could impact human technology, especially satellites and other spacecraft, making them more vulnerable to damage from solar storms and high-energy particles. The electrical grids on Earth might also experience disruptions due to induced currents from geomagnetic activity. Although a magnetic flip might sound alarming, it's essential to note that life on Earth has persisted through many such reversals over millions of years. However, these events can still pose challenges, requiring adaptation and mitigation strategies to protect technology and sensitive systems from the more immediate impacts during the transition period. Scientists continue to study rocks and sediments to understand better the patterns and effects of previous reversals, providing us with valuable insights into this fascinating aspect of Earth's dynamic nature. Antares, the bright red supergiant star in the constellation Scorpius, is one of the largest and most luminous observable stars in the night sky. It is nearing the end of its life and will eventually go supernova, an event that will be one of the most spectacular celestial displays witnessed from Earth. Fortunately, or unfortunately, depending on one's perspective, it's difficult to predict precisely when this dramatic event will occur. It could be tomorrow, or it might not happen for thousands of years. When Antares does go supernova, the explosion will be visible across much of the Earth, even during daytime, thanks to the immense amount of energy released. With a brightness potentially rivaling or even surpassing that of the full moon, the supernova will light up the sky for weeks or even months. During this time, Antares will temporarily outshine all other stars and could even be visible alongside the Sun. As the supernova's shockwave propagates through space, it will reveal intricate and beautiful details of stellar material being ejected at velocities of thousands of kilometers per second. For stargazers and scientists alike, such an event would be an unparalleled opportunity to study the life cycles of stars and the processes governing stellar explosions. Modern telescopes and observatories would capture detailed images and data, providing new insights into nucleosynthesis, the formation of heavier elements during explosive events. Even though Antares is located about 600 light-years away from us, its supernova will not pose any direct threat to Earth due to the considerable distance. Instead, it will offer an awe-inspiring spectacle and a wealth of scientific knowledge about our universe and its cosmic phenomena. The iconic and majestic rings of Saturn are among the most captivating features of our solar system. However, these rings are not permanent and are gradually disappearing. Scientists estimate that Saturn's rings may last only another 100 to 300 million years, a relatively short span in cosmic terms. When Saturn eventually loses its rings, the planet's appearance and some of its characteristics will undergo notable transformations. As the rings dissipate, primarily due to the process known as ring rain, where ring material falls into Saturn's atmosphere, the planet's visual majesty will diminish. Saturn will appear far less striking to observers on Earth and to future space missions. The loss of the rings also means a loss of the intricate dance of ice and rock particles that we've come to admire through telescopes and spacecraft imagery. These particles are gradually being pulled inward by Saturn's gravity and affected by the planet's magnetic field, contributing to a slow but steady process that will eventually result in a ringless Saturn. The absence of the rings will also lead to changes in Saturn's immediate environment. The rings contribute significantly to Saturn's albedo, or reflectiveness, and without them, the planet might appear somewhat dimmer when viewed from Earth. Additionally, the dynamics of Saturn's moons could be altered. Many of the moons interact gravitationally with the rings, and some ring material originates from the icy eruptions on moons like Enceladus. The disappearance of the rings could potentially affect the orbits and geological activity of Saturn's moons, though the full extent of such changes remains a subject of ongoing investigation. Ultimately, witnessing the transformation of Saturn as it loses its rings, albeit a process that will take millions of years, is a reminder of the ever-changing nature of our solar system. It underscores the dynamic processes that govern planetary bodies and their features, constantly reshaping what we consider as familiar and eternal in the cosmos. Interestingly, Mars, our neighboring red planet known for its stark landscapes and intriguing potential for past or present life, may one day acquire its own set of rings. This potential future development is tied to the fate of its moon Phobos, the larger of Mars' two moons. Phobos is gradually spiraling toward Mars at a rate of about 6 feet every 100 years due to gravitational interactions. Scientists predict that in approximately 30 to 50 million years, Phobos will reach a critical distance from Mars known as the Roche limit. At this point, the tidal forces exerted by Mars's gravity will become so strong that Phobos will be torn apart. The subsequent debris from this disintegration will spread out into a ring-like structure around Mars, resembling the elegant rings we currently attribute to Saturn. Initially, this ring might be a dense, rocky and dusty orbit around the planet, composed of fragments ranging from tiny particles to larger chunks. Over time, these particles would disperse and stabilize into a more defined ring structure. This process could be both fascinating and slow, potentially taking thousands to millions of years to fully develop. The resulting rings would not be as expansive or prominent as Saturn's. given Phobos's smaller size compared to the sources of Saturn's rings, but they would still present a remarkable spectacle. This transformation of Phobos into rings would offer scientists a unique opportunity to study similar processes that have occurred elsewhere in the solar system, providing insights into planetary ring formation, dynamics, and evolution. The eventual rings of Mars would not only alter the planet's appearance, but would also serve as a constant reminder of the dynamic and ever-changing nature of our celestial neighborhood. An extinction-level asteroid impact on Earth is a scenario often depicted in both scientific research and popular media, capturing our collective anxieties about the catastrophic potentials of space. Such an event, involving an asteroid larger than 5 to 10 kilometers in diameter, would unleash destruction on a scale beyond anything humanity has ever experienced. Upon impact, the initial explosion would generate immense heat, creating an enormous crater while vaporizing everything within hundreds of kilometers. The energy released would be equivalent to billions of tons of TNT, igniting widespread wildfires across continents as debris from the impact rained down. The shockwave would trigger powerful earthquakes and tsunamis, wreaking further havoc on a global scale. The aftermath, however, would be even more devastating. Dust, ash, and aerosols thrown into the atmosphere would block sunlight for months, possibly years, leading to a sharp drop in global temperatures in a phenomenon known as an impact winter. This dramatic climatic shift would disrupt weather patterns and significantly reduce photosynthesis, leading to massive crop failures and a collapse in food chains both on land and in the oceans. Many species, unable to adapt to the sudden and harsh conditions, would face extinction, echoing the fate of the dinosaurs 66 million years ago following the Chicxulub impact. Human civilization would be profoundly affected as infrastructure, agriculture, and social systems collapse. Famine, disease, and societal unrest could become widespread as resources dwindle and ecosystems crumble. Despite the grim outlook, humanity's advanced technology and global cooperation could offer some hope for survival and adaptation. Scientists and engineers have been exploring various strategies for planetary defense, such as diverting potential threats long before they can impact Earth. Proactive measures, including early detection systems and possible asteroid deflection missions, remain crucial to mitigating the risks posed by these celestial wanderers. An extinction-level impact serves as a humbling reminder of our planet's vulnerability and the importance of continued vigilance and scientific endeavor to protect our world from such unforgiving cosmic events. Gamma-ray bursts, GRBs, are among the most energetic and destructive events in the universe. These intense flashes of gamma rays can release more energy in a few seconds than our sun will emit over its entire lifetime. If a GRB were to occur relatively close to Earth, within a few thousand light years, and its beam were directed at our planet, the consequences would be severe and potentially catastrophic. The immediate impact of a nearby gamma ray burst hitting Earth would be the intense radiation influx. The atmosphere would absorb the gamma rays, leading to a process known as photodissociation, where high-energy photons break apart nitrogen molecules. This process would produce a significant amount of nitrogen oxides, depleting the ozone layer that protects life from harmful ultraviolet (UV) radiation from the sun. The temporary weakening or loss of the ozone layer would allow lethal doses of UV radiation to reach the surface, increasing the risk of cancers, genetic damage, and ecological disruptions. Furthermore, the cascade of radiation hitting Earth's atmosphere would create widespread ionization, leading to oxidative stress in living organisms and making the intricate biological systems vulnerable. This influx of gamma radiation could also result in a phenomenon known as ionospheric disturbance, which could disrupt communication systems, including satellite operations and radio transmissions. The altered atmospheric chemistry could lead to climatic changes, with potential repercussions for weather patterns and agricultural productivity. In addition to biological and climatic impacts, there is the possibility that the increased radiation could lead to more extensive darkening of the skies by producing extensive nitrogen dioxide clouds. This, akin to a global-scale smog, would further block sunlight, potentially causing a gamma-ray burst winter. The reduction in sunlight could lead to lower global temperatures, disrupt plant photosynthesis, and generate further ecological imbalances. Given these dire consequences, it's reassuring that GRBs are extremely rare events, and the likelihood of one occurring close enough to Earth to have such profound effects is very low. However, understanding such cosmic phenomena underscores the inherent vulnerability of life on our planet and the importance of astronomical research in monitoring and mitigating potential extraterrestrial threats. The study of gamma-ray bursts also reveals the dynamic and sometimes volatile nature of our universe, reminding us of the intricate balances that sustain life on Earth. The impending collision between our Milky Way galaxy and the Andromeda galaxy, a cosmic spectacle set to unfold over the next several billion years, promises to reshape our galactic neighborhood dramatically. With both galaxies hurtling toward each other at approximately 250,000 miles per hour, the event is a testament to the dynamic and ever-evolving nature of the universe. When the Milky Way and Andromeda finally collide, which scientists estimate will occur in about 4 to 5 billion years, the process will be anything but sudden. Instead, it will unfold over the course of several billion years, marked by several key phases. Initially, as the galaxies draw closer, their immense gravitational fields will begin to interact, pulling stars, gas clouds, and dark matter into elongated streams known as tidal tails. This first encounter will likely trigger bursts of star formation as clouds of hydrogen gas are compressed and ignite new stellar nurseries. As the galaxies continue to merge, they will pass through each other multiple times, causing significant distortion in their shapes. The once distinct spiral arms of both galaxies will be stretched and twisted into chaotic formations. During these interactions, some stars may be ejected into intergalactic space, while others may find themselves in vastly different orbits within the new galactic structure. Despite the dramatic nature of this collision, the vast distances between individual stars mean that direct stellar collisions will be rare. After several passes, the cores of the Milky Way and Andromeda, each harboring a supermassive black hole, will merge. This process will further funnel gas and stars into the central regions of the newly formed galaxy, possibly leading to a period of intense star formation and activity around the merged black hole. Over time, the two galaxies will settle into a new shape, likely forming a large elliptical galaxy, informally dubbed Milkomeda or Milkdromeda by astronomers. For any potential future civilizations witnessing this grand event from a safe vantage point, the night sky would offer a spectacular view filled with new clusters of stars and nebulae circling the merged galaxy. It's worth noting that our solar system is not expected to be directly threatened by the collision, although its position in the galaxy could be altered significantly. This galactic dance underscores the dynamism of the cosmos and the majestic forces that govern it. By studying such events, astronomers gain insight into the life cycles of galaxies and the intricate gravitational ballet that shapes our universe, reminding us of our place within this vast, interconnected tapestry. The phenomenon of Earth's days gradually becoming longer is primarily driven by the intricate gravitational interplay between our planet and its closest celestial neighbor, the Moon. Currently, Earth's days are increasing by about 1.7 milliseconds per century, a seemingly negligible amount, but one that accumulates over millions of years. This process, known as tidal friction, occurs because of the gravitational forces exerted by the Moon on Earth. As the Moon orbits our planet, it creates tidal bulges in Earth's oceans due to its gravitational pull. These bulges attempt to align with the Moon, but because Earth is rotating, they are slightly ahead of the Moon. This offset creates a torque, or rotational force, which transfers energy from Earth's rotation to the Moon's orbit. As a result, Earth's rotation slows down, while the Moon slowly moves away from Earth at a rate of about 3.8 centimeters per year. The energy transfer from Earth's rotational momentum to the Moon's orbital energy is a fascinating example of the conservation of angular momentum. As Earth loses angular momentum and slows down, the length of a day increases. Over billions of years, this process could lead to significantly longer days. For example, studies of ancient geological formations suggest that roughly 400 million years ago, a day on Earth was only about 22 hours long. In addition to tidal friction, other factors also contribute, albeit to a lesser extent, to the lengthening of Earth's days. These include the gravitational interactions with the Sun and other planets, as well as internal processes within Earth itself, such as the redistribution of mass caused by glaciation, earthquakes, and mantle convection. In the grand scheme of cosmic events, the gradual lengthening of Earth's days reminds us of the dynamic nature of our planet. It highlights the continuous and subtle influences of gravitational forces and celestial movements that shape our world's journey through time. As days lengthen, they provide a poignant testament to the intricate and ever-evolving dance between Earth and its lunar companion, an orbital ballet that has persisted for billions of years and will continue far into the future. The Sun, like all stars, goes through a life cycle that includes birth, stability, and eventually death. Over the course of billions of years, our Sun will undergo several significant transformations as it exhausts its fuel and approaches the end of its life. Here's a glimpse into the stages of the Sun's transformation as it dies. In its current stage, the Sun is a stable main-sequence star, fusing hydrogen into helium in its core. This phase, which began roughly 4.6 billion years ago, is marked by relative stability and will continue for another approximately 5 billion years. During this time, the Sun will gradually increase in luminosity and size as it exhausts its hydrogen fuel. The first major transformation will occur when the Sun depletes its core hydrogen supply and begins to fuse helium. The core will contract under gravity, heating up and causing the outer layers to expand. This will turn the Sun into a red giant, a phase during which it will swell to possibly engulf the orbits of Mercury and Venus, and potentially Earth. The Sun's outer layers will cool and turn red, while the core becomes hot enough to start fusing helium into carbon and oxygen. After the red giant phase, the Sun will shed its outer layers, creating a shell of gas and dust known as a planetary nebula. This beautiful glowing cloud will expand outward, illuminated by the remaining core of the Sun. The shedding of mass will significantly reduce the Sun's gravitational influence on the remaining planets. The Sun's core, now exposed, will become a white dwarf. Composed mostly of carbon and oxygen, this dense, Earth-sized remnant will no longer undergo nuclear fusion, but will gradually cool and fade over billions of years. The white dwarf will emit residual heat but will not generate new energy, leading it to slowly dim. Eventually, it will become a black dwarf, a theoretical stage that is so far unobserved because the universe isn't old enough for any white dwarfs to have cooled entirely. Throughout these stages, the solar system will undergo dramatic changes. The inner planets, if not engulfed during the red giant phase, will be stripped of their atmospheres and scorched by the increased luminosity. The outer planets may experience altered orbits due to the Sun's reduced mass and gravitational pull. The transformation of the Sun as it dies is a reminder of the cosmic cycles that govern stars. While the process will span billions of years, its culmination will mark the end of the Sun's role as a life-giving star, leaving behind a legacy of elements that contribute to the ongoing creation and evolution of the universe. As the Sun transitions into a red giant, the solar system will undergo profound and dramatic changes that will irreversibly alter its structure and the conditions of its celestial inhabitants. This transformation is expected to occur in roughly 5 billion years, as the Sun exhausts its hydrogen fuel and begins to fuse helium in its core. The effects of this red giant phase will be far-reaching. The most immediate and obvious change will be the Sun's significant expansion. As it swells to hundreds of times its current diameter, it may engulf the orbits of the closest planets, Mercury and Venus. For Earth, the situation is more speculative. While it might be consumed by the expanding Sun, it's more likely that it will be subjected to intense heat and radiation, resulting in the complete evaporation of its oceans and the stripping away of its atmosphere. The once habitable planet would become a scorched, barren rock, resembling the current state of Mercury. Mars, which lies further out, might temporarily find itself within the habitable zone, albeit far too briefly to foster any significant life. The increased solar intensity would dramatically heat its surface, potentially causing the sublimation of polar ice caps and triggering atmospheric changes. However, these conditions would not last, as Mars too would eventually become inhospitable. The scale of the Sun's expansion will also affect the outer planets and the icy bodies of the Kuiper Belt. The increased solar wind and radiation pressure could cause significant changes in the atmospheres and surfaces of the gas giants, Jupiter, Saturn, Uranus, and Neptune. For example, the outer atmospheres of these planets could experience increased temperatures, resulting in dynamic weather patterns and possibly even shrinking due to lost hydrogen and helium. The solar wind from the red giant sun will intensify, carrying away vast amounts of stellar material into space. This mass loss will reduce the sun's gravitational pull, causing the orbits of the remaining planets to drift outward. The entire architecture of the solar system could be altered, with the moons and smaller bodies experiencing changed orbits and dynamic environments as a result of the shifting gravitational forces. As the sun sheds its outer layers towards the end of the red giant phase, forming a beautiful planetary nebula, the solar system will lose a significant portion of its mass. This nebula will enrich the surrounding interstellar medium with elements forged within the sun, contributing to the cosmic cycle of star formation and planetary systems. Ultimately, the solar system that emerges from the sun's red giant phase will be starkly different from the one we know today. It will be marked by the remnants of planetary bodies orbiting a cooling white dwarf, the final stage of the sun's evolution. While this distant future may seem almost unfathomable, studying such transformations helps us understand the life cycles of stars and the long-term future of planetary systems, providing a deeper appreciation for the dynamic and intricate processes that govern our universe. When the sun completes its transformation and becomes a white dwarf, it will mark the final phase of its stellar evolution. This dense Earth-sized remnant will be composed primarily of carbon and oxygen, no longer undergoing nuclear fusion, and will continue to cool and dim over time. The transition to a white dwarf will bring about several profound changes to the solar system. Initially, the process leading up to the white dwarf stage involves the sun shedding its outer layers during the red giant phase, forming a planetary nebula. This nebula will be a spectacular display of glowing gas illuminated by the hot core of the sun, now exposed as a white dwarf. As this nebula expands and disperses into interstellar space, it enriches the surrounding medium with elements created during the sun's lifetime, contributing to the ongoing cycle of star formation and planetary development in the galaxy. The reduced mass of the sun as a white dwarf, which is about 55% of its original mass, will result in weaker gravitational pull. This will significantly alter the orbits of the remaining planets, causing them to drift farther from the sun. The stable, predictable orbits that characterize the current solar system will be replaced by a more tenuous and dispersed arrangement. Some of the outer planets, like Jupiter and Saturn, might retain their roughly stable orbits but farther from the sun, while the inner planets may have already been engulfed during the red giant phase. For Earth, if it survives the red giant phase, its prospects will be bleak. With no heat or light from the now cooled white dwarf, Earth will become a frozen wasteland, devoid of the possibility of sustaining life as we know it. Any residual atmosphere would have long since been stripped away, and the surface temperatures would plummet to extremes, leaving a lifeless and cold relic. The gas giants, Jupiter and Saturn, along with their moons, would similarly experience drastic cooling. Without the sun's radiant heat, the icy moons of these planets would freeze even further, locking in any subsurface oceans that might have existed. The distant Kuiper Belt and Oort cloud, populated with icy bodies, would remain relatively unchanged in this new, darker solar system, but would orbit a far dimmer central star. In the longer term, the white dwarf will continue to cool over billions of years, steadily fading as it loses residual heat. Eventually, it may become a black dwarf, a hypothetical final state in which it no longer emits any significant heat or light. However, this stage is purely theoretical, as the universe is not yet old enough for any white dwarfs to have reached this fully cooled state. The transformation of the sun into a white dwarf concludes its life cycle and signifies a transition of the solar system into a quieter, colder, and darker state. This distant future scenario underscores the fleeting nature of stellar and planetary phenomenons, reminding us of the intricate and ever-changing dynamics of our cosmic environment. By understanding these processes, we gain valuable insights into the life cycles of stars and the evolutionary trajectory of planetary systems, providing a humbling perspective on our place within the vast expanse of the universe. The orbits of the planets in our solar system are not static. They are subject to various gravitational interactions and perturbations that will gradually alter them over billions of years. These changes arise from a combination of factors, including the gravitational influences of neighboring planets, the Sun's evolving characteristics, and external galactic forces. Here's how these orbital changes might unfold over such immense timescales. In the near term, spanning millions to a few billion years, planetary orbits will slowly alter due to gravitational interactions among the planets themselves. Jupiter, the most massive planet in our solar system, plays a particularly significant role in these dynamics. Its enormous gravitational field can cause tiny adjustments to the orbits of other planets through a process known as secular perturbation. While these changes are minute over short timescales, over billions of years, they can lead to more noticeable modifications. For example, Earth's orbit will gradually become more eccentric and less circular, changing its distance to the Sun over its annual cycle. Tiny but continual shifts driven by the gravitational tugs from Venus and Jupiter can alter the shape and orientation of Earth's orbit, potentially impacting long-term climate patterns. Mars, similarly, will experience shifts in its orbital eccentricity driven by interactions with Jupiter and, to a lesser extent, Earth. As the Sun evolves and transitions through its red giant phase, its mass will significantly decrease due to the loss of outer layers. By the time the Sun becomes a white dwarf, it will retain about 55% of its original mass. The reduction in mass will weaken the Sun's gravitational pull, causing the orbits of the planets to expand. This mass loss means that the remaining planets, such as Jupiter, Saturn, Uranus, and Neptune, will move farther away from the Sun. Their orbits will become more elongated, creating a more dispersed and less tightly bound solar system. The inner planets, if they survive the Sun's red giant phase, will find their orbits significantly altered. Mercury and Venus are highly likely to be engulfed by the expanding Sun, while Earth could either be swallowed or stripped of its atmosphere and scorched, rendering it uninhabitable and altering its orbit as mass loss continues. Furthermore, the solar system does not exist in isolation. It moves through the Milky Way galaxy, encountering various gravitational influences, such as passing stars and molecular clouds. Over billions of years, these galactic encounters can perturb the outer regions of the solar system, particularly affecting the orbits of distant bodies in the Kuiper Belt and Oort cloud. Occasionally, a passing star could exert enough gravitational force to send comets and asteroids streaming into the inner solar system, or even eject them entirely into interstellar space. Long-term predictions become increasingly complicated due to chaotic interactions and cumulative effects. While precise projections become impossible beyond a certain point, it is clear that the planet's orbits will continue to evolve in response to the complex interplay of internal and external forces. Over billions of years, the solar system will witness significant changes in the orbits of its planets due to gravitational interactions, the Sun's mass loss, and external galactic influences. These transformations highlight the dynamic and ever-changing nature of our cosmic environment, offering a humbling perspective on the immense timescales and forces at play in shaping our solar neighborhood. The Sun's increasing luminosity, a natural consequence of its aging process, is projected to have profound effects on Earth, altering our planet in ways both subtle and dramatic. As the Sun grows older, it gradually burns its hydrogen fuel at a faster rate, leading to an increase in energy output. This increased luminosity, even if appearing modest on a cosmic timescale, will cause significant changes in the Earth's climate over hundreds of millions of years. In the next 100 million years alone, Earth's average temperatures will rise considerably, leading to the evaporation of bodies of water and a decrease in atmospheric carbon dioxide as the carbon cycle becomes disrupted. Consequently, the heat-trapping efficacy of our planet's atmosphere will diminish, ultimately making Earth a less hospitable place for life as we know it. This gradual increase in solar energy will have cascading effects on Earth's biosphere and geology. Spoiler alert for the distant future. As temperatures climb, the heat will accelerate the silicate weathering process, whereby carbon dioxide is removed from the atmosphere and stored in the form of carbonate minerals. This geological mechanism, which has kept Earth's climate stable for eons, will ironically reach a point where it depletes atmospheric carbon dioxide to levels insufficient for photosynthesis. Plants, the bedrock of the terrestrial food web, will suffer, leading to the collapse of ecosystems long before oceanic evaporation turns our planet into a parched expanse. This dramatic forecast underscores the delicate balance in which life on Earth exists, perpetually sustained by the intricate interplay between our planet and its stellar companion. As the solar system evolves, the asteroid belt, located between the orbits of Mars and Jupiter, will also undergo significant transformations. Currently, the asteroid belt is comprised of countless rocky fragments and debris, the remnants of planetesimals that never coalesced into a full-fledged planet due to Jupiter's gravitational interference. However, this seemingly static belt is anything but immutable. Over billions of years, gravitational perturbations from Jupiter and occasional collisions between asteroids will continue to alter the distribution and composition of these rocky bodies. As the Sun evolves from a middle-aged star into a red giant and eventually sheds its outer layers to become a white dwarf, the overall mass and gravitational pull of the Sun will decrease. This reduction in gravitational force could cause the orbits of asteroids in the belt to become more eccentric, leading to increased chances of collisions and subsequent fragmentation. Additionally, the shift in gravitational dynamics might propel a significant number of asteroids out of the belt, potentially sending them on new trajectories throughout the solar system. Interestingly, as the Sun enters its red giant phase, its expanding outer layers might directly envelop some parts of the asteroid belt, particularly the innermost regions. The intense solar winds during this phase could act like a cosmic broom, sweeping away smaller particles and dramatically thinning out the belt. Conversely, the remaining larger asteroids could become more isolated, drifting in wider, more erratic orbits as the gravitational landscape of the solar system continues to change. These evolving conditions paint a dynamic and ever-changing picture of the asteroid belt, echoing the larger transformative processes at work within our celestial neighborhood. In the distant future, the Kuiper Belt, a vast region of space beyond Neptune brimming with icy bodies and dwarf planets, will also experience substantial changes as the solar system continues to evolve. Currently, the Kuiper Belt is home to a variety of objects, including well-known bodies like Pluto and Eris, that orbit the Sun in a relatively stable yet distant manner. However, as the Sun ages and undergoes significant transformations, the stability of the Kuiper Belt will be challenged. As the Sun expands into a red giant, the outer reaches of the solar system, including the Kuiper Belt, will not be directly engulfed, but the increased solar radiation and solar winds will have notable effects. The Sun's mass loss during this phase, particularly when it evolves into a white dwarf, will result in a decrease in its gravitational hold on the solar system. This reduced gravitational influence will cause the orbits of Kuiper Belt objects to expand, becoming more eccentric and potentially perturbed by the gravitational effects of nearby celestial bodies. Consequently, some objects may be ejected from the Kuiper Belt entirely, either being flung into interstellar space or redirected inward towards the inner solar system. Furthermore, interactions with passing stars and galactic tidal forces could stir the Kuiper Belt, altering the orbital dynamics of its constituents. These external forces may result in increased collisions among Kuiper Belt objects, leading to more fragmentation and the creation of smaller debris. Such interactions could also perturb some objects into entering the inner solar system, becoming what we observe as long-period comets. As the Milky Way galaxy continues its own evolution, including a likely collision with the Andromeda galaxy, the gravitational perturbations on the Kuiper Belt will become even more pronounced, further dispersing these distant icy bodies. In the end, while the Kuiper Belt will persist as a component of our solar system, its character will be markedly altered. The once semi-stable population of icy worldlets will be scattered and reshuffled by the cosmic forces at play, transforming this distant region into a dynamic arena of ongoing celestial change, part of the broader narrative of our solar system's enduring evolution. The Oort cloud, a vast spherical shell of icy bodies encircling the solar system at a great distance, is considered the source of long-period comets. It lies far beyond the orbits of the Kuiper Belt and the planets, extending possibly halfway to the nearest stars. This distant reservoir of icy objects will be significantly influenced by the gravitational forces exerted by passing stars over the eons. As stars pass near the solar system, an event that happens periodically on cosmic timescales, their gravitational influence can perturb the orbits of the objects within the Oort cloud. These stellar flybys can induce a variety of effects, from minor alterations in orbital paths to dramatic ejections of these icy bodies from the cloud. Such perturbations increase the likelihood of some objects being nudged out of their distant orbits and sent plunging into the inner solar system as long-period comets, becoming visible to inhabitants of planets like Earth. History tells us that many of the most spectacular comets seen from Earth originate from the Oort cloud, dislodged by these very interactions with passing stars. Moreover, the collective gravitational forces from numerous nearby stars over the course of millions and billions of years can gradually reshape the Oort cloud. These interactions may result in a more dispersed and elongated cloud, rather than the relatively spherical one postulated today. In extreme cases, particularly close encounters with stars or even with rogue planets wandering the galaxy, portions of the Oort cloud could be entirely stripped away, joining the interstellar medium or being captured by other star systems. Ultimately, the Oort cloud's fate is intricately linked to the dynamic environment of our galaxy. As the Sun and its stellar neighbors orbit around the Milky Way, the ongoing gravitational ballet ensures that the Oort cloud remains a dynamic and ever-changing frontier, influenced by the proximity and movement of stars across the galactic landscape. This ceaseless interaction highlights the interconnectedness of celestial objects, revealing a cosmos in constant ebb and flow. As the Sun approaches the final stages of its life cycle, the fate of the outer planets, Jupiter, Saturn, Uranus, and Neptune, will be dramatically influenced by the transformations occurring within our star. When the Sun exhausts the hydrogen in its core, it will expand into a red giant, significantly increasing in size and shedding a substantial portion of its mass through intense solar winds. This mass loss will reduce the gravitational grip the Sun has on all the planets, including those in the outer reaches of the solar system. During the red giant phase, the solar system's dynamics will shift. The reduced gravitational pull will prompt the outer planets to migrate outward, adopting wider orbits. Jupiter and Saturn, possessing substantial gravitational fields themselves, may perturb each other's orbits, as well as those of Uranus and Neptune, to a lesser extent. Despite these changes, the outer planets are likely to remain relatively intact due to their significant distances from the Sun. They will not face the extreme heating or potential engulfment that the inner planets will endure. As the Sun transitions from a red giant to a white dwarf, this capability-spanning transformation will have far-reaching effects. Once the Sun sheds its outer layers and settles into a dense, Earth-sized white dwarf, the solar wind will cease, and the outer planetary migration initiated during the red giant phase will stabilize. The white dwarf will exert much less gravitational force compared to the Sun in its current state, leading to a more loosely bound solar system where the outer planets continue their expanded orbits. In this new celestial order, the outer planets will cool over billions of years as they drift further from their now diminished stellar companion. The absence of significant solar radiation will freeze any remaining atmospheric activity, turning these gas giants into even more inert spheres of gas and ice. The planetary moons, especially those like Titan and Europa, which harbor subsurface oceans, could also undergo drastic changes as their environments cool and stabilize in this extended stellar twilight. The fate of these distant worlds underscores the broader narrative of solar system evolution, reflecting the intricate dance between stars and their satellite systems across the eons. As the Sun evolves through its life cycle, the nature and intensity of the solar wind will undergo significant transformations, impacting the entire solar system in the process. Currently, the solar wind, composed primarily of a stream of charged particles such as protons and electrons, emanates from the Sun's corona and affects space weather, planet atmospheres, and the heliosphere's boundary with interstellar space. However, this benign, steady-state wind is set to change as the Sun ages. In its current middle-aged phase, the solar wind is relatively stable, reaching speeds of up to over 1 million miles per hour and influencing the magnetic fields and atmospheres of planets in its path. As the Sun runs out of hydrogen fuel in its core and enters the red giant phase, the solar wind will become much more intense. The Sun's outer layers will expand massively, with the solar wind increasing in both velocity and density. During this phase, the solar wind will strip away the outer atmospheres of nearby planets. Earth itself will suffer not only from increased solar radiation, but also from this intensified solar wind, which will erode its magnetic field and atmosphere over time. As the Sun transitions from a red giant to the white dwarf phase, it will shed a significant part of its mass in the form of solar wind and other stellar winds, creating a planetary nebula. This intense period of mass loss will eventually give way to the more stable, albeit diminished, state of a white dwarf. In this last evolutionary stage, the Sun's energy output, including its solar wind, will dramatically lessen. The once robust outflow will taper off to a trickle compared to its former self, substantially reducing the pressure on the heliosphere. This reduction will cause the boundary of the heliosphere to shrink, altering the dynamics of the interstellar interaction. As the solar wind diminishes, the outer planets and the interstellar medium will begin to have a greater influence on this heliospheric boundary. In essence, the Sun's protective bubble, created by its solar wind, will become less effective at shielding the solar system from interstellar cosmic rays. Overall, the changes in the solar wind throughout the Sun's life will reflect the broader evolutionary journey of our star, marking each stage with distinct challenges and transformations for the solar system's structure and dynamics. After the Milky Way and Andromeda galaxies collide, an event predicted to occur in about 4 billion years, the night sky will undergo a spectacular transformation, presenting a cosmic light show visible from any vantage point in the newly formed galaxy, often termed Milkomeda or Milkdromeda. Initially, as the two galaxies draw near, the night sky will become an intricate tapestry of stars, showcasing a larger and brighter Andromeda galaxy that will progressively dominate the night sky with its approach. This gravitational ballet will cause tidal forces to distort both galaxies, creating vast tidal tails of stars and gas that stretch across the heavens. During the collision, the night sky would be a chaotic, awe-inspiring sight. The galactic cores, each harboring a supermassive black hole, will dance around each other in a complex gravitational interplay. This celestial dance will trigger intense star formation in regions where gas clouds collide, resulting in starburst regions that will shine brightly. Massive bands of newly formed stars will light up the sky, and nebulae illuminated by these newborn stars will add vibrant patches of color to the cosmic panorama. Over millions of years, as the two galaxies merge, the process will trigger an abundance of supernovae from massive stars formed during these starbursts, each outshining entire galaxies for short periods and adding transient points of brilliance to the nightscape. Once the merger stabilizes, the night sky will look markedly different from today's. The Milky Way's characteristic spiral structure will be replaced by a more elliptical shape. The central region will be denser and brighter due to the fusion of the two galaxies' stellar bulges. The amalgamation will result in a thick, dense core filled with older, redder stars, surrounded by an elongated halo of stars dispersed over vast distances. The constellations familiar to us now would have radically reconfigured, and celestial landmarks like globular clusters will rearrange or possibly dissipate into the new galactic structure. In this transformed sky, observers would experience a night sky filled with a higher density of stars, especially toward the galactic center. The combined galaxy would not just be a blend of the Milky Way and Andromeda's stars, but enriched by new generations of stars born from their combined interstellar medium. Amidst this stellar tapestry, the larger elliptical core will glow quietly, a testament to the grand cosmic collision that reshaped the heavens, creating a celestial spectacle that would be the wonder of any stargazer fortunate enough to witness it. The forthcoming merger between the Milky Way and the Andromeda galaxy will be an epical event, transforming both galaxies into a single unified structure over the course of billions of years. The initial stages of this galactic collision, expected to begin in about 4 billion years, will be characterized by dramatic tidal forces that will stretch and distort both galaxies. As Andromeda approaches, it will dominate the night sky, creating tidal tails composed of stars and gas, drawn out by mutual gravitational forces. These tidal features will make the night sky appear highly dynamic and ever-evolving. During the collision, both galaxies will lose their distinct spiral shapes. Their interstellar gas clouds will collide, compressing to form new stars in regions of intense starburst activity. This burst of star formation will light up the night skies with clusters of bright young stars and supernova explosions. The gravitational interactions will send many stars into new orbits, disrupting the established patterns, and could potentially eject some stars entirely, flinging them into intergalactic space. As the cores of the Milky Way and Andromeda draw inexorably closer, their central supermassive black holes will also begin to interact. Eventually, these black holes are expected to merge in a cataclysmic event, releasing enormous amounts of energy in the form of gravitational waves. This merger will mark the final unification phase of the galaxy's cores, creating a single, more massive, supermassive black hole at the heart of the newly formed galaxy. In the billions of years following the initial collision, the remnant stars from both galaxies will settle into a new, more stable configuration. By this time, the new galaxy, often referred to as Milkomeda or Milkdromeda, will have shed the spiral structures that characterize the Milky Way and Andromeda, instead forming a large elliptical galaxy with a dense, bright core. The newly combined galaxy will be populated by older, redder stars in its central bulge, surrounded by a sprawling halo of stars dispersed through its outer regions. The collision will also affect the distribution of dark matter, which plays a crucial role in the gravitational dynamics of galaxies. The dark matter halos of both galaxies will merge, forming a more extensive halo that encompasses the new galaxy and influences its overall gravitational structure. This transformation will change how the galaxy interacts with nearby satellite galaxies and other objects in the local group. Overall, while the galactic merger will obliterate the distinct identities of the Milky Way and Andromeda, it will create a new, massive elliptical galaxy, marking an extraordinary chapter in the cosmic history of our local universe. This process will not only redefine the structure and appearance of our galaxy, but also serve as a testament to the incredible, ever-changing nature of the cosmos. The passage of a rogue star through the solar system would be a cataclysmic event with far-reaching consequences. A rogue star, one that has been ejected from its home galaxy or is simply wandering through interstellar space due to gravitational interactions, could significantly disrupt the delicate gravitational balance that governs our solar system. As the rogue star approaches, its gravitational influence would begin to perturb the orbits of the outer planets, such as Neptune and Uranus, potentially causing them to deviate from their established paths. Depending on the star's mass and proximity, these gravitational effects could cascade inward, affecting the orbits of Saturn, Jupiter, and even the terrestrial planets like Earth. The closer the star, the more pronounced these disturbances would be, potentially leading to elongated or highly eccentric orbits for some planets. In the extreme scenario where the rogue star passes very close to the Sun, the gravitational disruption could be so severe that it might eject some planets from the solar system entirely. Smaller bodies like asteroids and comets, particularly those residing in regions like the Kuiper Belt and the Oort cloud, would also experience significant perturbations. This gravitational shakeup could send a barrage of these objects hurtling towards the inner solar system, raising the likelihood of catastrophic impacts on Earth and other planets. Moreover, the rogue star's passage could trigger intense tidal forces within the planetary moons, particularly those like Europa and Enceladus that have subsurface oceans. The resultant internal heating could lead to increased volcanic and tectonic activity, drastically altering their geologic landscapes. Aside from gravitational influences, the rogue star's radiation could also have direct impacts. If it were a particularly luminous star, the increased radiation could affect planetary atmospheres, causing dramatic changes in climate and atmospheric chemistry. In the unlikely event that the rogue star had any companion planets or debris, it could introduce these objects into our solar system, adding to the chaotic environment. As the rogue star eventually moves away, the solar system would be left in a state of tumultuous readjustment. Planets would settle into new orbits, some potentially on collision courses with other bodies, while ejected objects could wander aimlessly through interstellar space. The long-term effects would be profound, reshaping the architecture of the solar system and potentially posing existential risks to life on Earth. The intrusion of a rogue star into our solar system would be a highly disruptive event, altering orbital dynamics, triggering potential collisions, and significantly impacting the stability of planetary environments. Such an event underscores the fragile equilibrium that governs our cosmic neighborhood and the potential for dramatic changes wrought by external forces wandering through the galaxy. The distribution of stars in the galaxy is a dynamic process that evolves over billions of years, driven by a variety of astrophysical phenomena. As stars are born, live out their life cycles, and eventually die, their positions and populations continually shift, reshaping the galactic landscape. Initially, stars are born in massive molecular clouds located within the spiral arms of the galaxy. These nurseries give birth to clusters of stars due to the gravitational collapse of gas. Over time, these clusters disperse as their stars drift apart, influenced by gravitational interactions with other stars and the overall galactic potential. As a result, the distribution of stars extends further out into the galaxy, contributing to the gradual thickening of the galactic disk. As stars age, their life cycles introduce additional dynamics into the galactic mix. Massive stars with their relatively short lifespans end in spectacular supernova explosions, enriching the surrounding interstellar medium with heavy elements. These supernovae not only inject energy into the galactic environment, but also trigger new waves of star formation, perpetuating the cycle of stellar birth and death. Meanwhile, stars in the disk experience a phenomenon known as radial migration, where they gradually drift outward or inward from their original birthplaces. This process occurs due to the gravitational perturbations caused by spiral arms and other large-scale structures within the galaxy. Over billions of years, this migration adds to the mixing of stellar populations, distributing stars across different regions of the galactic disk. At the same time, interactions with satellite galaxies and other external influences play a role in shaping the stellar distribution. For example, the Milky Way's gravitational interactions with the Sagittarius dwarf galaxy and the Magellanic Clouds contribute to the formation of stellar streams, long trails of stars that arc through the galaxy. These interactions can also inject new stars into the halo and outer regions of the galaxy, further diversifying the stellar population. In the galactic center, stars undergo a different set of dynamics. The central bulge is densely populated with older, redder stars, along with the supermassive black hole that dominates the core. Over time, the dynamical relaxation processes cause stars in the central regions to move towards a more thermodynamically stable distribution, potentially resulting in a more spheroidal configuration. As galaxies like the Milky Way age and experience mergers with other galaxies, their overall structure changes. The future collision with the Andromeda Galaxy will be a significant event that will dramatically alter the distribution of stars. As the two galaxies merge and their stars interact, the resultant galaxy will have a more elliptical shape, with stars redistributed into a massive spheroidal configuration. Many stars will be ejected into the outer halo or even into intergalactic space, while others settle into new orbits within the newly formed galactic structure. Ultimately, the distribution of stars in the galaxy is a complex, ever-changing phenomenon influenced by internal dynamics, external interactions, and the galaxy's ongoing evolution. Over billions of years, these factors will transform the spatial distribution of stars, continually reshaping the galaxy's appearance and structure. A supernova occurring in our galactic neighborhood, a distance typically considered to be within a few hundred light-years from Earth, would have profound and potentially severe effects on our planet and the broader solar system. Supernovae are among the most energetic and explosive events in the universe, resulting from the catastrophic death of a massive star. The energy released in such explosions can far outshine an entire galaxy for a brief period, and the resultant shockwave and radiation can have far-reaching consequences. One immediate effect of a nearby supernova would be a significant increase in high-energy radiation, including gamma rays, X-rays, and cosmic rays. These energetic particles can penetrate the Earth's atmosphere, potentially causing widespread damage to the ozone layer, which protects life from the sun's ultraviolet radiation. A weakened or depleted ozone layer would lead to an increase in UV radiation reaching the surface, causing heightened levels of skin cancer, DNA mutations, and other harmful biological effects. The influx of cosmic rays from a supernova can also ionize the atmosphere, leading to the formation of nitrogen oxides that could further deplete the ozone layer. Additionally, these atmospheric changes may result in alterations to climate patterns, potentially causing disruptions in weather systems and affecting global temperatures. Moreover, increased cosmic ray exposure can pose a direct threat to technological infrastructure, such as satellites and power grids, by inducing electrical currents and potentially causing malfunctions or failures. From an astronomical perspective, a nearby supernova would be an extraordinary event to observe. The supernova would appear as an extraordinarily bright object in the sky, visible even during the daytime. This brightness could persist for weeks to months, gradually fading as the exploded star's remnants disperse. The event would provide invaluable data to scientists studying stellar evolution, nucleosynthesis, the formation of new elements, and the dynamics of such enormous explosions. In the longer term, the remnants of a supernova contribute to the enrichment of the interstellar medium with heavy elements, seeding future generations of stars and planetary systems with the building blocks necessary for the formation of planets and potentially life. These supernova remnants, consisting of rapidly expanding clouds of gas and dust, can trigger the formation of new stars as they collide with surrounding molecular clouds, compressing the gas and reigniting the cycle of stellar birth. However, if a supernova were to occur extremely close to Earth, within just a few dozen light-years, the effects could be catastrophic, potentially leading to mass extinctions. Historical records and geological evidence suggest that past extinction events on Earth may have been influenced or even caused by such nearby stellar explosions. Overall, while a supernova in our galactic neighborhood would be a spectacular astronomical event, its effects on Earth could range from significant atmospheric alterations and increased radiation exposure to potentially catastrophic biological impacts, underscoring the delicate balance in which life on our planet exists in the vast and dynamic cosmos. In densely packed regions, such as globular clusters or the cores of galaxies, stars interact with each other far more frequently and dynamically than in sparser areas, such as the outskirts of a galaxy like the Milky Way. These interactions can lead to a variety of fascinating and complex phenomena, driven by the close proximity of numerous stellar bodies. One of the most common forms of interaction in such regions is gravitational encounters. Stars in densely packed environments can pass close enough to one another that their mutual gravitational forces significantly alter their trajectories. These close encounters can result in stars being deflected into new orbits, sometimes ejecting them from the dense region altogether, or causing them to dive deeper into the core. In extreme cases, high-energy close encounters can lead to stellar collisions, which, although rare, can produce dramatic outcomes such as the formation of more massive stars or the ejection of stellar material into space. Additionally, stars in these crowded environments can exchange or capture companions, leading to the formation of binary or multiple star systems. In such systems, stars can transfer mass to one another, affecting their evolutionary paths. For example, a larger, more evolved star can transfer material onto a smaller companion, causing the companion to brighten and potentially whiting out the donor star's outer layers. This mass transfer process can also lead to the formation of exotic objects like blue stragglers, stars that appear younger and hotter than others in the same population because they have gained mass from a companion. Another intriguing phenomenon in densely packed regions is the formation of stellar exotica such as millisecond pulsars, low-mass X-ray binaries, and even intermediate-mass black holes. The frequent dynamical interactions and close encounters in these regions can cause neutron stars or white dwarfs to capture companions from which they can accrete matter. This accretion can spin up neutron stars to millisecond periods or lead to intense X-ray emission from the accretion processes. Binary encounters involving two or more stars can lead to the formation of tightly bound systems, creating sources of intense gravitational radiation detectable by observatories like LIGO and Virgo. In the core regions of galaxies where supermassive black holes reside, stars are subject to even more extreme gravitational forces. Interactions in these environments can lead to stars being shredded by tidal forces if they wander too close to the central black hole, a phenomenon known as tidal disruption events. These events can produce incredible flares of radiation as the stellar material is accreted onto the black hole. Finally, densely packed stellar environments are also ideal sites for the formation and interaction of interstellar medium features. The close proximity of numerous stars, particularly massive ones, enriches the surrounding space with heavy elements through supernova explosions and stellar winds. These processes can lead to the formation of new stars as the enriched material condenses, perpetuating a cycle of stellar birth and death. Densely packed regions are hotbeds of stellar activity and interaction, hosting a range of dynamical processes that lead to the formation of exotic objects, the transfer of mass between stars, and the continuous reshaping of their stellar populations. These environments serve as natural laboratories for studying the complex and often violent interplay between stars, providing critical insights into the mechanisms that drive stellar evolution and the architecture of the cosmos. A close encounter with another star would be a dramatic event for our solar system, with potentially profound consequences. The gravitational forces exerted by the passing star could significantly disrupt the delicate balance that holds our planetary system together. As the rogue star approaches, its gravitational influence would initially perturb the orbits of objects in the outer reaches of the solar system, such as those in the Oort cloud and the Kuiper belt. These regions, home to countless icy bodies and cometary nuclei, could experience scattering effects, sending some objects hurtling toward the inner solar system while ejecting others into interstellar space. As the rogue star continues to draw nearer, the gravitational disruptions would become more pronounced, affecting the orbits of the outer planets, Neptune, Uranus, Saturn, and Jupiter. The precise nature of these perturbations would depend on various factors, including the mass, speed, and trajectory of the passing star. In some scenarios, the massive outer planets could experience changes in their orbits, potentially leading to more elliptical or inclined paths. Such changes would have cascading effects on the entire solar system due to the gravitational interrelationships among the planets. Closer to the Sun, the inner planets, including Earth, could also be affected, although to a lesser extent. Even slight alterations in Earth's orbit could have significant consequences for our climate and habitability. Changes in orbital distance could result in more extreme seasons or fluctuations in global temperatures, potentially disrupting ecosystems and challenging the continuity of life on Earth. In extreme cases, a closely passing star might even lead to the ejection of planets from the solar system. If the gravitational forces are strong enough, one or more planets could be flung into interstellar space, becoming rogue planets themselves. Conversely, the passing star might capture one or more of our solar system's planets, adding them to its own retinue. The presence of the rogue star would also increase the likelihood of collisions and impacts. Perturbed orbits in the Kuiper belt and Oort cloud could send a shower of comets and asteroids into the inner solar system, dramatically increasing the risk of impacts on Earth and other planets. Such an influx of impactors could have devastating consequences, with the potential to cause mass extinctions and alter the course of life on our planet. Additionally, the magnetic fields and stellar winds of the passing star could interact with those of the Sun, potentially affecting the heliosphere, the protective bubble formed by the solar wind that shields the solar system from interstellar radiation. These interactions might compress or distort the heliosphere, exposing the solar system to higher levels of cosmic radiation and further stressing planetary atmospheres. Once the rogue star moves away, the solar system would slowly settle into a new configuration, but the gravitational and dynamical disruptions would leave a lasting imprint. The altered orbits, changed planetary positions, and reconfigured debris fields would result in a fundamentally different solar system from the one we know today. In summary, a close encounter with another star would be a cataclysmic event for our solar system, characterized by significant gravitational perturbations, potential ejections or captures of planets, increased collision risks, and lasting changes to planetary orbits and the overall structure of the system. This scenario underscores the delicate balance that governs our cosmic neighborhood and the profound impact external forces can have on our solar system's stability and configuration. The structure of the Milky Way galaxy will undergo substantial changes over billions of years, influenced by a variety of internal and external factors. As time progresses, the dynamic processes governing stellar formation, gravitational interactions, and galactic mergers will reshape our galaxy, creating new patterns and structures. One of the most significant long-term changes will be driven by the upcoming collision with the Andromeda galaxy, predicted to occur in about 4 billion years. This monumental event will dramatically transform the Milky Way. Initially, the two galaxies will approach each other, disrupting their spiral structures through mutual gravitational forces. As they collide, Tidal tails composed of stars and gas will stretch out from both galaxies, producing a chaotic and spectacular night sky. During the merger, intense gravitational interactions will trigger waves of star formation, fueled by the compression of gas clouds. These regions of new stars, called starburst regions, will temporarily brighten parts of the galaxy. The supermassive black holes at the centers of the Milky Way and Andromeda will eventually coalesce, resulting in a more massive black hole that will dominate the core of the newly formed galaxy, often referred to as Milkomeda or Milkdromeda. As the merger continues, the distinct disk-like spiral structures of both galaxies will gradually dissipate, giving way to a more spheroidal or elliptical shape. The central bulge will become denser and more elongated, filled with older, redder stars. The outer regions will form a sprawling halo of stars, incorporating some of the stellar populations from both the Milky Way and Andromeda. This new galactic structure will be more dynamically relaxed, with stars settling into orbits that create a large elliptical system. Apart from the Andromeda collision, the Milky Way will also continue to interact with smaller satellite galaxies and star clusters. These gravitational interactions will lead to the accretion of smaller galaxies, adding their stars and material to the Milky Way. Over time, these mergers will enrich the galactic halo with additional stars and dark matter, further altering the galaxy's mass distribution and dynamics. In terms of internal processes, the Milky Way will see a gradual decline in star formation activity as the available gas is consumed or expelled. The depletion of gas will slow down the birth of new stars, transitioning the galaxy to a phase where the majority of stars are older and less luminous. Massive stars that formed earlier will have ended their lives in supernova explosions, contributing to the enrichment of the interstellar medium with heavier elements. These supernova events will continue to influence the galactic environment, but their frequency will diminish over time. In the galaxy's core, interactions between stars and the central supermassive black hole will drive energetic phenomena such as accretion flares and the formation of high-velocity stars. These processes will contribute to the evolution of the galactic nucleus, shaping its structure and activity. On an even longer timescale, interactions with neighboring galaxies in the local group, including the Triangulum galaxy, will influence the Milky Way's evolution. Although these interactions will be less dramatic than the Andromeda merger, they will still contribute to the overall reshaping of the galaxy's structure. Over billions of years, the Milky Way will transform from a spiral galaxy into a more spheroidal or elliptical structure due to the merger with Andromeda and ongoing gravitational interactions with other galaxies and satellite systems. These changes will be marked by periods of intense star formation, reconfiguration of stellar orbits, and the accretion of new material, ultimately resulting in a galaxy that is markedly different from the one we inhabit today. A black hole passing near our solar system would have profound and potentially catastrophic effects. The exact consequences would depend on the black hole's mass and distance during its closest approach, but even a relatively distant passage could have significant impacts due to the extreme gravitational forces exerted by these enigmatic objects. Firstly, as the black hole approaches, its gravitational pull would begin to perturb the orbits of objects in the outer solar system, including those in the Kuiper Belt and Oort cloud. These regions, rich in comets and other icy bodies, would experience gravitational scattering. This scattering could send a deluge of comets into the inner solar system, dramatically increasing the likelihood of impacts on planets, including Earth. Such an influx of comets could trigger catastrophic events, akin to the one hypothesized to have led to the extinction of the dinosaurs. For the outer planets, Neptune, Uranus, Saturn, and Jupiter, the black hole's approach would create significant gravitational disturbances. These planets could experience alterations in their orbits, potentially becoming more eccentric or inclined. In extreme cases, one or more of these planets might be ejected from the solar system entirely, turning them into rogue planets wandering through interstellar space. As the black hole draws closer to the inner solar system, its gravitational influence would become even more pronounced. The orbits of the inner planets, Mercury, Venus, Earth, and Mars, could be destabilized, resulting in changes to their orbital paths. Even slight deviations in Earth's orbit could have severe consequences for its climate and habitability. Changes in orbital eccentricity could lead to more extreme seasons or long-term climatic shifts, challenging the survival of life on our planet. Should the black hole come very close, the tidal forces could induce significant geological activity on the planets and their moons. The intense gravitational gradients could trigger increased volcanic activity, earthquakes, and tectonic shifts, reshaping planetary surfaces. Moons, particularly those with subsurface oceans like Europa and Enceladus, could experience enhanced tidal heating, potentially affecting their internal structures and geysers. In addition to gravitational effects, a black hole passing near the solar system could impact the heliosphere, the bubble-like region dominated by the solar wind that surrounds our solar system. The alterations in gravitational fields could reshape the heliopause, the boundary between the solar wind's influence and interstellar space. The compression or distortion of the heliosphere could expose the solar system to higher levels of cosmic radiation, affecting planetary atmospheres and potentially increasing radiation exposure on Earth. If the black hole were to pass even closer or through the solar system, the consequences would be dire. The extreme gravitational forces could disrupt the orbits of planets to such an extent that they might collide with one another or be torn apart. The immense tidal forces could spaghettify smaller objects, stretching them out into long, thin shapes as they are pulled toward the black hole. This scenario, though highly unlikely, represents the most extreme outcome of a black hole encounter. Once the black hole moves away, the solar system would take a long time to stabilize. The altered orbits of planets, potential loss of celestial bodies, and increased impacts from comets and asteroids would result in a solar system markedly different from its original state. The long-term stability of planetary orbits could remain compromised, leading to an era of continued dynamical chaos. A black hole passing near our solar system would fundamentally disrupt the architecture and stability of the system. Its gravitational influence would perturb orbits, potentially ejecting planets, increasing collision risks, and altering the heliosphere. The geological and climatic impacts on Earth and other planets could be severe, posing existential threats to life and potentially reshaping the solar system for billions of years to come. When galaxies interact, they often undergo dramatic transformations that can significantly affect their star formation rates. These cosmic encounters can range from gentle gravitational dances to violent collisions. One of the most intriguing aspects of galactic interactions is their ability to trigger starbursts, periods of intensely heightened star formation. During these interactions, the gravitational forces between galaxies can compress vast clouds of hydrogen gas, the raw material for star creation. As these gas clouds are squeezed, they collapse more readily under their own gravity, igniting a flurry of new star births. Some interactions, like the famous collision between the Milky Way and the Andromeda Galaxy predicted to occur in roughly 4.5 billion years, are expected to spark such a starburst phase. Conversely, while the onset of interaction might stimulate star formation, prolonged interactions can have the opposite effect. As galaxies merge, their combined gravitational forces can eventually heat up and disperse the gas that fuels star formation. This gas, crucial for the birth of new stars, is often expelled into the intergalactic medium or consumed by already existing stars, leading to a decline in star formation rates. The Milky Way, with its rich tapestry of ongoing mergers and collisions, provides a fascinating laboratory for studying these dynamic processes. Understanding these interactions not only enlightens our view of galactic evolution, but also reveals the delicate balance of forces that sculpt the cosmos. The future prospects for discovering Earth-like exoplanets are incredibly promising, thanks to advancing technology and innovative missions designed to probe the farthest reaches of our galaxy. Over the past few decades, the quest to find planets beyond our solar system has already yielded over 4,000 confirmed exoplanets, many of which reside in the so-called habitable zone, where conditions could potentially support liquid water and perhaps life. NASA's Kepler Space Telescope set the stage, and its successor, the Transiting Exoplanet Survey Satellite, or TESS, continues to discover planets by monitoring the brightness of nearby stars. As TESS homes in on characteristics like size and orbit that could indicate Earth-like qualities, astronomers are becoming increasingly adept at identifying candidates for further study. The upcoming James Webb Space Telescope, JWST, set to launch into orbit, will revolutionize this search even further. With its advanced spectrometers and unparalleled resolution, JWST will be able to analyze the atmospheres of these exoplanets, looking for signs of habitability such as water vapor, oxygen, and methane. Meanwhile, ground-based observatories like the extremely large telescope in Chile will complement these efforts, achieving unprecedented detail through adaptive optics technology. Looking further ahead, planned missions like the Wide-Field Infrared Survey Telescope, WFIRST, and the European Space Agency's Plato mission aim to refine our search techniques and expand our catalogue of Earth-like worlds. Given the exponentially increasing pace of discovery, we are on the brink of potentially identifying a true Earth twin within the next few decades, fundamentally altering our understanding of life's place in the universe. As stars age, their habitable zones, the regions where conditions might be right for liquid water to exist on a planet's surface, undergo significant changes. In the early stages of a star's life, particularly if it's a sun-like star, the habitable zone is relatively close to the star itself. During its main sequence phase, a star converts hydrogen into helium in its core, maintaining a relatively stable luminosity. For our Sun, this stability has allowed Earth to remain within its habitable zone for billions of years. However, a star's luminosity gradually increases as it ages, causing its habitable zone to slowly shift outward. As a star exhausts its hydrogen fuel and begins to burn heavier elements, it moves into the red giant phase, expanding dramatically. In this phase, the outer layers of the star swell and the habitable zone moves much farther out. Planets that were once frozen in the outer reaches could briefly find themselves in a newly established habitable zone. However, this phase is often short-lived on a cosmic scale, and the intense radiation from the swollen star can strip away atmospheres, making sustained habitability challenging. Ultimately, for Sun-like stars, the transformation into a white dwarf marks the end of significant habitable zone shifts. The residual heat from white dwarfs can sustain faint habitable zones close to the star for some time, but these zones are not as conducive to life as those during the star's main sequence phase. In summary, habitable zones are dynamic, shifting outward as stars age and undergo various stages of their life cycles. The stability of these zones is crucial for the long-term potential for life on any orbiting planets, underscoring the interdependent dance between stellar evolution and planetary habitability. As our understanding of these processes becomes more refined through observation and modeling, we gain deeper insights into where to look for life beyond our solar system. Exoplanets in red dwarf systems present a fascinating array of long-term evolutionary challenges and opportunities for habitability. Red dwarfs, also known as M-dwarfs, are the most common type of star in our galaxy. They are smaller and cooler than stars like our Sun, with surface temperatures ranging between 2,000 and 3,500 Kelvin. These stars have extraordinarily long lifespans, often stretching into the trillions of years, which provides a lengthy window for potential habitability. Yet this longevity is coupled with unique challenges posed by their stellar activity, especially during their early years. In the youthful phase of red dwarfs, they tend to emit powerful flares and intense ultraviolet and X-ray radiation. This high-energy radiation can have significant impacts on the atmospheres of closely orbiting exoplanets. In some instances, sustained stellar activity could strip away these atmospheres entirely, especially if the planets lack sufficient magnetic fields to provide protection. Over time, however, red dwarfs typically settle into a more stable phase with reduced stellar activity, potentially allowing atmospheres to regenerate or stabilize, particularly if the planets have significant volcanic activity or other outgassing processes to replenish their atmospheres. Another critical factor for exoplanets in red dwarf systems is tidal locking. Due to their proximity to the cooler stars to remain within the habitable zone, many planets orbiting red dwarfs are tidally locked, meaning one side of the planet perpetually faces the star while the other remains in constant darkness. This can create extreme temperature gradients and atmospheric dynamics. Advanced climate models suggest that a thick atmosphere capable of efficient heat redistribution or substantial oceans could mitigate these extremes, potentially offering habitable conditions even on tidally locked worlds. In conclusion, while red dwarf systems pose unique long-term changes and challenges for exoplanets, They also offer tantalizing opportunities for the study of habitability in diverse environments. As our detection techniques improve and we gather more data on these intriguing systems, our understanding of the potential for life in the universe continues to expand, revealing just how adaptable life might be across different cosmic landscapes. The death of a host star brings dramatic transformations to its exoplanetary system, reshaping the fates of its accompanying planets. The destiny of these systems hinges on the type of star and the manner of its demise. For Sun-like stars, those with masses up to roughly 8 times that of our Sun, the end comes through a transition into a red giant phase, shedding its outer layers to form a planetary nebula and finally contracting into a white dwarf. During the red giant phase, any planets within the inner part of the system, potentially including those in the habitable zone, could be engulfed or subject to severe atmospheric stripping from intense solar winds and radiation. As the star sheds mass, the gravitational balance of the system changes, potentially pushing remaining planets into more distant orbits. Once the star has become a white dwarf, it retains some of its gravitational influence but with significantly reduced luminosity. The habitable zone, now much closer to the faint white dwarf, offers little refuge for life as we know it. Nevertheless, researchers speculate that under the right conditions, some planets might migrate inward to these new, narrower habitable zones, though sustaining life would be highly challenging. Interestingly, the cooling process for white dwarfs is extremely slow, lasting billions of years, so planets or moons with subsurface oceans, analogous to Europa or Enceladus in our solar system, might maintain liquid water under their icy crusts for extended periods, possibly harboring some form of life. For more massive stars, those over 8 solar masses, their life ends in a supernova explosion. This explosive end obliterates nearby planets and dramatically alters or erases the architecture of the planetary system. The remnant, a neutron star or a black hole, could still gravitationally clutch some outer planets or planetary debris. In rare instances, surviving exoplanets may continue to orbit these stellar remnants in stable, though highly transformed systems. These transformative processes underline the dynamic, ever-evolving nature of the cosmos. Through studying the life cycles of exoplanetary systems, even post-stellar death, we gain invaluable insights into the resilience and adaptability of planetary bodies within our universe. Interactions between exoplanets and their stars evolve significantly over time, shaped by a complex interplay of gravitational forces, magnetic fields, and stellar activity. In the early stages of a planetary system's formation, the protoplanetary disk, comprising gas, dust, and other materials, plays a crucial role. Young, energetic stars emit strong stellar winds and radiation that can dissipate this disk, affecting the migration and final positioning of exoplanets. Close-in exoplanets, particularly gas giants known as hot Jupiters, can experience significant inward or outward migration due to gravitational interactions with the disk and other forming planets. As the star and planets settle into more stable orbits, the gravitational interactions continue to evolve, often leading to resonances where planets exert regular, periodic gravitational influences on each other. Over long periods, these resonances can drive shifts in orbital eccentricities and inclinations, sometimes resulting in dramatic changes such as planetary collisions or ejections from the system entirely. In multi-planet systems, the dynamic gravitational interplay can also stabilize certain orbits, allowing for a delicate balance that persists for billions of years. For planets in closer orbits, tidal interactions with their host stars become increasingly significant. Tidal forces can cause planets to synchronously rotate, showing the same face to their star, a phenomenon seen in many of the exoplanets orbiting red dwarfs, as well as in our own moon's relationship with Earth. Over extended timescales, these tidal interactions can result in tidal heating, which may influence geological activity and potentially support conditions amenable for hosting life. Conversely, these interactions can also lead to orbital decay, slowly drawing the planet closer to the star. Magnetic interactions add another layer of complexity, particularly for stars with strong magnetic fields. Stellar winds and magnetic fields can strip away atmospheres from close-in planets, fundamentally altering their surface conditions and potential habitability. For stars with higher activity levels, such as young red dwarfs, Intense magnetic interactions can lead to significant space weather events, affecting planetary atmospheres and potentially thwarting habitability efforts. The evolutionary trajectory of interactions between exoplanets and their stars is a multifaceted dance influenced by gravitational, tidal, and magnetic forces. This intricate interplay shapes the long-term stability, atmospheric evolution, and potential habitability of these distant worlds, providing a rich tapestry of research opportunities that continue to deepen our understanding of planetary systems, both near and far. The future discovery of rogue exoplanets, planets that float freely in space unbound to any particular star, holds immense potential to expand our understanding of planetary formation and evolution. Rogue exoplanets are believed to originate in planetary systems, but are subsequently ejected due to complex gravitational interactions or chaotic dynamical processes. Detecting these elusive wanderers has been challenging, but advancements in technology and observational techniques are opening new frontiers. One promising method for future rogue planet discoveries is gravitational microlensing. This phenomenon occurs when a rogue planet passes in front of a distant star, bending and magnifying the star's light due to the planet's gravitational field. The ongoing and future missions like the Nancy Grace Roman Space Telescope, slated for launch in the mid-2020s, aim to exploit this technique. Roman will monitor millions of stars in the Milky Way, potentially uncovering hundreds or even thousands of rogue exoplanets by detecting the subtle changes in starlight that they cause. Another avenue for discovery is through direct imaging with next-generation telescopes, such as the James Webb Space Telescope, extremely large ground-based observatories like the Giant Magellan Telescope, and future space missions like the European Space Agency's Gaia Observatory and WFIRST. These powerful instruments could detect rogue planets by their faint heat signatures, particularly those that are relatively young and still cooling from their formation. The detection capabilities will be enhanced by advanced image processing algorithms and adaptive optics systems that minimize the distortions caused by Earth's atmosphere. Beyond mere detection, studying rogue exoplanets could reveal much about the extreme conditions and diversity of planetary environments. These planets, free from the illuminating heat of a nearby star, may have unique atmospheric compositions or surface conditions shaped by internal heat sources. Some theories even suggest that rogue planets might harbor subsurface oceans, kept liquid by geothermal heat, offering intriguing possibilities for life in the most unexpected corners of our galaxy. In conclusion, the potential future discoveries of rogue exoplanets promise to significantly broaden our understanding of planetary science, offering insights into how planets form, evolve, and survive in the cosmos. With evolving technologies and ambitious space missions on the horizon, the next few decades could bring a wealth of new knowledge about these mysterious wanderers, further fueling our quest to comprehend the vast and varied tapestry of worlds that populate our universe. Tidal forces will play a crucial role in shaping the futures of moons orbiting exoplanets, influencing their orbits, internal dynamics, and even their potential habitability. These forces arise from the gravitational interaction between a moon, its host planet, and in some cases the exoplanet's host star. Over long periods, tidal interactions can lead to significant changes that impact the geological and atmospheric characteristics of these moons. One primary consequence of tidal forces is tidal heating, which occurs as the gravitational pull of the planet causes continuous flexing of the moon's interior. This process can generate considerable heat, potentially driving volcanic activity and maintaining subsurface oceans beneath icy crusts. A well-known example in our solar system is Jupiter's moon Europa, where tidal heating is believed to sustain a vast subsurface ocean. Similarly, moons of exoplanets undergoing strong tidal interactions could harbor internal liquid water environments, making them intriguing candidates for studies of astrobiological potential. Tidal forces also influence the rotational dynamics of moons. Over time, these forces can lead to synchronous rotation, where the moon's rotational period matches its orbital period around the planet, resulting in one hemisphere constantly facing the planet. This phenomenon, observed in our own moon's orbit around Earth, can have profound effects on the moon's climate and geological activity by creating stark differences between the near and far sides, impacting factors like surface temperature distribution and potential habitability zones. Orbital decay is another critical outcome of tidal forces. For moons orbiting very close to their host exoplanets, tidal interactions can cause their orbits to gradually shrink. In extreme cases, this inward spiral could lead to a catastrophic end, with the moon eventually colliding with the planet or being torn apart by tidal forces, forming rings similar to those seen around Saturn. Conversely, for moons in more distant orbits, tidal interactions can work to enhance orbital stability, possibly protecting these moons from such destructive fates. In multi-moon systems, gravitational interactions between moons can further complicate the tidal dynamics. Resonances between their orbits can amplify or mitigate tidal effects, influencing long-term orbital stability. Advanced theoretical models and future observations will be essential in understanding these complex interactions, offering insights into the evolutionary pathways of moons in diverse exoplanetary systems. Overall, the future of moons orbiting exoplanets will be profoundly shaped by the intricate dance of tidal forces, impacting their geological activity, orbital characteristics, and potential as havens for life. As our detection methods and observational technologies improve, we will gain a clearer picture of these fascinating worlds and their dynamic interactions, enhancing our understanding of the universe's multifaceted nature. The discovery of exoplanets in multi-star systems, a phenomenon once considered rare but now recognized as relatively common, has profound implications for our understanding of planetary formation, stability, and potential habitability. These systems, which can range from binary stars to more complex configurations involving 3 or more stellar bodies, present unique environments where the gravitational influences of multiple stars can significantly affect the evolutionary pathways of orbiting exoplanets. One major implication involves the dynamics of planetary formation. Traditional models of planet formation are typically based on single star systems, but the presence of multiple stars introduces additional gravitational forces that can alter the distribution of gas and dust in the protoplanetary disk. These altered conditions can influence where and how planets form, potentially leading to different types of planetary systems. For instance, planets in multi-star systems might form further out from their primary star, or in some cases, within the disk that is influenced by the gravitational pull of all stars in the system. The stability of planetary orbits in multi-star systems is another critical consideration. The gravitational interplay between multiple stars can lead to complex and sometimes unstable orbital configurations for planets. In binary systems, planets can have stable orbits if they are either very close to one of the stars, S-type orbits, or far enough away from both stars to orbit around their common center of mass, P-type orbits. However, if planets reside in intermediate zones, their orbits might become chaotic, resulting in potential ejection from the system or collisions with other bodies. Advanced computational models are essential for predicting these stability zones and understanding the long-term behavior of such planetary systems. The potential habitability of exoplanets in multi-star systems also presents intriguing possibilities and challenges. The varying distances and changing angles of illumination from multiple stars can lead to significant fluctuations in a planet's climate. For instance, a planet might experience periods of extreme heat followed by intense cooling, depending on the orbital dynamics of its host stars. These climatic variations could impact the development and sustainability of life. However, the presence of multiple stars could also contribute to a broader range of habitable zones, potentially increasing the chances for life-supporting conditions. Finally, the diversity observed in multi-star systems expands our understanding of the universe's complexity. These systems challenge our preconceived notions of planetary architecture and demonstrate the robustness and adaptability of planetary formation processes. They provide invaluable laboratories for testing theories about planet formation, migration, and stability, offering insights that single-star systems alone cannot. In conclusion, the implications of finding exoplanets in multi-star systems are far-reaching, influencing our theories of planetary formation and stability, as well as expanding the potential habitability of planets under diverse conditions. As technological advancements enhance our ability to detect and study these fascinating systems, we will continue to uncover the rich tapestry of possibilities inherent in multi-star planetary systems, furthering our quest to understand the intricate workings of the cosmos. Planetary collisions are dramatic events that can profoundly shape the future of exoplanetary systems, influencing their structure, composition, and long-term evolution. These cataclysmic interactions occur when gravitational forces bring planets into close proximity, resulting in impacts ranging from minor grazes to violent mergers. One of the most significant effects of planetary collisions is the alteration of planetary orbits. When planets collide, the resulting debris and kinetic energy can cause shifts in the orbits of remaining bodies within the system. These changes can lead to increased orbital eccentricity and inclination, destabilizing the system's architecture. Over time, these destabilizations can prompt further collisions or planetary ejections, radically transforming the system's structure. For example, a collision might result in the formation of smaller debris that coalesces into moons or rings, or it may scatter smaller planetary fragments across the system, impacting other bodies and potentially contributing to further collisions. The compositional changes resulting from planetary collisions also have long-lasting implications. Impacts can strip away atmospheres, alter surface geology, and mix material from the colliding bodies. Such events can reset the clock on planetary development, stripping away significant portions of a planet's crust or mantle and revealing deeper layers. This can lead to a reformation period where the planet's geological and atmospheric conditions evolve anew. In some cases, collisions might deliver volatile compounds like water, potentially creating new environments where life could eventually arise. In terms of planetary formation, collisions play a critical role in the accretion process, particularly during the early stages of planet formation. In the chaotic environment of a protoplanetary disk, smaller planetesimals frequently collide and merge, gradually building up into larger planetary bodies. Giant impacts are thought to have played a significant role in shaping our own solar system, including the formation of the Moon and the differentiation of Earth's layers. Similar processes likely occur in other planetary systems, leading to the diverse array of exoplanets we observe. Another profound implication of planetary collisions is their impact on habitability. While such collisions are often catastrophic, they can also lead to the creation of new, potentially habitable environments. For instance, a collision might strip away a thick, inhospitable atmosphere, exposing a more temperate surface below. Alternatively, the heat generated from the impact could create transient oceans or subsurface water reserves, providing niches where life might develop. However, frequent or particularly violent collisions could also render a planet inhospitable, constantly resetting any complex ecosystems that attempt to take hold. Planetary collisions are pivotal events that shape the future of exoplanetary systems in myriad ways. They influence orbital dynamics, planetary composition, system architecture, and even potential habitability. As we continue to study exoplanets and their systems, understanding the role of collisions will be crucial in piecing together the complex history and evolution of these distant worlds, enriching our broader comprehension of the universe's intricate workings. The prospects of detecting signs of advanced extraterrestrial civilizations have captivated human imagination and scientific inquiry for decades. As our technology and observational capabilities continue to advance, the search for extraterrestrial intelligence, SETI, remains one of the most compelling and profound endeavors in modern science. There are several promising avenues through which we might detect signs of advanced civilizations in the near future. One of the primary methods is through the detection of technosignatures, artificial signals or artifacts of technology, such as radio transmissions. The SETI Institute and other organizations have been scouring the sky for decades using radio telescopes, aiming to detect non-natural, structured signals that could indicate the presence of intelligent life. The advent of more powerful and sensitive radio telescopes like the Square Kilometre Array, SKA, expected to become partially operational in the mid-2020s, dramatically increases our ability to detect faint or distant signals across vast swathes of the sky and frequency spectrum. Optical SETI is another promising approach, involving the search for laser pulses or other forms of coherent light that might be used by an advanced civilization for communication or signaling. These searches harness sophisticated photon detection equipment to identify brief, intense flashes of light against the backdrop of stars. The Breakthrough Listen initiative, for instance, is a significant investment aimed at pushing the boundaries of both radio and optical searches for intelligent life. Infrared astronomy offers an exciting prospect as well. Advanced civilizations might harness vast amounts of energy, potentially detectable as waste heat in the form of infrared radiation. Projects like the James Webb Space Telescope, JWST, and future infrared observatories could help detect excess infrared emissions from exoplanets or structures around stars, such as the hypothetical Dyson spheres, megastructures that could encompass a star to capture its energy output. Another avenue of exploration is through the search for technosignatures related to a civilization's impact on planetary atmospheres. Future telescopes with high-resolution spectroscopy capabilities, such as the soon-to-be-launched James Webb Space Telescope and potential missions like the LUVOIR, Large UV Optical IR Surveyor, will enable detailed study of exoplanetary atmospheres. Scientists could look for signs of industrial pollutants or other chemical anomalies that suggest technological processes. Gravitational wave astronomy, while still in its infancy, presents a futuristic prospect. Advanced civilizations might engage in activities that generate detectable gravitational waves, such as moving large masses or utilizing warp drives. Detectors like the Laser Interferometer Gravitational Wave Observatory, LIGO, and its successors could, in the distant future, explore these speculative signals. Emerging methods also involve the concept of searching for megastructures or other large-scale engineering projects. Space-based telescopes capable of direct imaging could potentially identify large, non-natural structures in the vicinity of stars, adding a new dimension to the search for extraterrestrial intelligence. In conclusion, the future prospects for detecting signs of advanced extraterrestrial civilizations are becoming increasingly promising due to rapid advancements in technology and innovative methods in observational astronomy. From searching for radio and optical signals to examining infrared signatures and atmospheric anomalies, these endeavors push the boundaries of our knowledge and imagination. While the challenge remains monumental, the potential discovery of intelligent life beyond Earth would revolutionize our understanding of the universe and our place within it. In a billion years, the universe will continue its inexorable march towards greater complexity and expansion, bringing about significant, albeit often subtle, changes in the cosmic landscape. One of the most profound transformations will be driven by the ever-accelerating expansion of the universe, influenced by dark energy. As galaxies drift farther apart, the observable universe will appear more sparsely populated. Some distant galaxies that we can currently observe will recede beyond the cosmic horizon, becoming undetectable even with the most powerful telescopes. Within our own Milky Way galaxy, stellar evolution will proceed at its characteristic pace. Many young, massive stars that are currently shining will have exhausted their nuclear fuel and exploded as supernovae, leaving behind neutron stars, black holes, or dispersing their enriched material into the interstellar medium. This ongoing cycle of birth, life, and death of stars will gradually increase the metallicity of the galaxy, contributing to the formation of new generations of stars and planetary systems. For the solar system, significant changes are also anticipated. Our Sun, currently around halfway through its life, will continue to shine much as it does today. However, in about 5 billion years, it will undergo a dramatic transformation into a red giant, a process that will not yet have begun in a billion years, but is gradually approaching. During this intermediate period, Earth will face increased solar luminosity, gradually becoming hotter. In approximately a billion years, the habitable zone will move outward, rendering Earth potentially inhospitable for life as we know it. The oceans may evaporate entirely, and surface temperatures could rise to levels that preclude the presence of liquid water, profoundly impacting any remaining biospheres. In the broader cosmic theater, galaxy interactions and mergers will continue to play a pivotal role. The Milky Way and the nearby Andromeda Galaxy, both members of the local group, are predicted to be on a collision course, though this event lies beyond the billion-year mark. However, the gravitational interactions leading up to this eventual merger will begin to influence the dynamics and structure of both galaxies in subtle ways, reshaping their distributions of stars, gas, and dark matter. The expansion of the universe will also affect the cosmic microwave background, CMB, the afterglow of the Big Bang. While its direct impact won't be pronounced within a billion-year time frame, the continued redshifting of the CMB will render it even cooler and its signal fainter, gradually blending into the general microwave noise of the universe. Culturally and scientifically, if intelligent civilizations, including potentially our own, still exist a billion years from now, their understanding of the universe will be vastly more advanced. They might possess the capability to traverse vast cosmic distances, manipulate fundamental forces, or even harness resources on truly astronomical scales. The search for extraterrestrial intelligence might yield diverse forms of life or advanced societies, fundamentally altering our cosmic perspective and relationship with the universe. The universe in a billion years will be shaped by ongoing cosmic expansion, stellar evolution, and the dynamic interactions of galaxies. The observable cosmic environment will gradually become more sparse and cooler, while our own galaxy and system will undergo significant evolutionary changes. These natural processes, coupled with the potential advances of intelligent civilizations, set the stage for an ever-transforming and increasingly enigmatic cosmos. The cosmic microwave background, CMB radiation, the relic radiation from the Big Bang, will undergo several notable changes over time, primarily driven by the ongoing expansion of the universe. As the universe continues to expand, this ancient radiation will progressively redshift, causing its wavelength to stretch and its temperature to decrease even further. Currently, the CMB is observable in the microwave region of the electromagnetic spectrum with an average temperature of approximately 2.725 Kelvin. Over the next billion years, as the universe expands, the wavelength of the CMB photons will continue to stretch, shifting them further into the radio part of the spectrum. This redshifting process leads to a cooling effect. As the CMB photons stretch, their energy diminishes, causing the background temperature to drop. In a billion years, the temperature of the CMB will be slightly cooler than it is today, though the drop over such a period will be modest compared to its dramatic cooling over the past 13 billion years since the Big Bang. The gradual decrease in the temperature of the CMB will also mean that the radiation will become weaker and more diffuse, making it increasingly challenging to detect. As this faint signal stretches into the longer wavelengths, specialized techniques and instruments will be required to observe and study it. Future advances in radio astronomy and detector technology will be essential for continuing to extract valuable cosmological information from this weakening signal. Another significant change involves the influence of matter and energy distribution on the CMB. The large-scale structures of the universe, such as galaxy clusters and superclusters, will continue to evolve and may alter the anisotropies, the tiny fluctuations in temperature and density imprinted on the CMB. These fluctuations hold vital clues to the early conditions of the universe and the formation of cosmic structures. As matter clumps together over time due to gravitational attraction, the gravitational lensing effect on the CMB will increase, causing distortions in the CMB maps that need to be accounted for to maintain accurate cosmological models. The Sunyaev-Zeldovich effect, where high-energy electrons in galaxy clusters distort the CMB by scattering its photons, will persist and potentially become more pronounced with the continued formation of large-scale structures. This effect makes certain regions of the CMB appear hotter or cooler than they would be otherwise, and provides important information about the distribution of hot gas in the universe. Ultimately, the fate of the CMB is tied to the eventual fate of the universe. If the current rate of acceleration driven by dark energy persists, the observable universe will continue to expand, causing the CMB to redshift even further until it becomes nearly undetectable. Far into the future, it might fade into an almost undetectable background of weak radio waves. In conclusion, the cosmic microwave background radiation will continue to redshift and cool over time due to the expansion of the universe, gradually transitioning into the radio spectrum and becoming increasingly faint and diffuse. These changes, while gradual over the next billion years, reflect the dynamic and ever-evolving state of the cosmos, providing ongoing opportunities to deepen our understanding of the universe's origins and ultimate fate. The concept of the heat death of the universe, also known as the Big Freeze, represents a possible ultimate fate for the cosmos, wherein the universe asymptotically approaches a state of maximum entropy. In this scenario, thermodynamic processes effectively come to a halt, leading to a universe that is uniformly cold, dark, and lifeless. This theoretical endpoint has profound implications for the nature of matter, energy, and the very notion of time and existence. At the heart of the heat-death hypothesis is the second law of thermodynamics, which states that in any closed system, entropy, a measure of disorder, tends to increase over time. As the universe continues to expand, stars will gradually exhaust their nuclear fuel and cease to shine. Stellar remnants, such as white dwarfs, neutron stars, and black holes, will eventually cool and fade. Without the creation of new stars, galaxies will grow darker and colder over eons. As energy sources peter out, the matter will continue to decay in various ways. For instance, proton decay, a hypothetical process predicted by some grand unified theories, could cause atomic nuclei to break down over trillions of years, further contributing to the dispersal of matter. Even the most stable particles may eventually decay, leading to a diffuse and nearly homogeneous spread of particles and radiation. Black holes, which represent some of the densest concentrations of matter, will play a unique role. While they might initially dominate the cosmic landscape, they will themselves evaporate over extremely long timescales through a process known as Hawking radiation, releasing any remaining energy back into the universe. This gradual evaporation process will cause even the mightiest black holes to eventually disappear, leaving behind a vacuum populated by low-energy photons and other subatomic particles. In a universe approaching heat death, thermal equilibrium will be reached, meaning temperature differences will vanish, and no usable energy will remain to power processes that increase order or sustain life. The universe will be in a state of thermal equilibrium, characterized by a uniform temperature very close to absolute zero. This implies that all physical processes, including those that sustain biological and mechanical systems, will effectively come to a standstill. For any form of life or civilization, the implications are profound and bleak. Civilizations rely on energy gradients to perform work, from biological processes to advanced technological endeavors. In a universe heading for heat death, these energy gradients will diminish and ultimately disappear, making it impossible to sustain any form of organized complexity. This casts a shadow on the long-term prospects for life, intelligence, or any ordered structure. Furthermore, the passage of time itself becomes somewhat meaningless in the context of a uniformly cold, inert universe. With no events or processes to mark the flow of time, the concept of time as we understand it ceases to have practical relevance. In conclusion, the heat death of the universe signifies a future in which entropy reaches its maximum, resulting in a uniformly cold, dark, and static cosmos. The implications of this scenario touch upon the fundamental nature of matter, energy, and time, highlighting an inevitable drift toward disorder and equilibrium. While the timeframes involved are unimaginably long, contemplating the heat death reinforces the transient nature of the cosmos and the ephemeral existence of stars, galaxies, and potentially even life itself. Dark energy is one of the most enigmatic components of our universe, and it plays a crucial role in driving the accelerated expansion of the cosmos. Its exact nature remains mysterious, but its influence on the universe's expansion is profound and will continue to shape the future of cosmology. Here's an overview of how dark energy is expected to influence the universe as we move forward in time. Dark energy is believed to constitute about 68% of the total energy content of the universe. Its effects became apparent in the late 20th century when observations of distant supernovae showed that the expansion of the universe is accelerating. Prior to this discovery, it was thought that the expansion might be slowing down due to the gravitational pull of matter. Dark energy, however, exerts a repulsive force that counteracts gravitational attraction on large scales, leading to an ever-increasing rate of expansion. As the universe continues to expand, the influence of dark energy will become even more dominant. In models where dark energy is a cosmological constant, as described by the lambda term in the lambda cold dark matter or LCDM model, its density remains constant even as the universe expands. This results in an exponential acceleration of the cosmic expansion. Galaxies will recede from each other at faster and faster rates, leading to a future where distant galaxies disappear beyond the cosmic horizon. This horizon is the maximum distance from which light can arrive at an observer. As the expansion accelerates, more galaxies cross this horizon, rendering them invisible, effectively isolating galaxy groups from each other. For local galaxies that remain gravitationally bound, such as the Milky Way and the Andromeda Galaxy, and their local group members, dark energy will have a subtler influence. these galaxies will eventually merge due to their mutual gravitational attraction, forming a massive elliptical galaxy. Within this local structure, stellar evolution will continue as stars age, die, and new stars are born. But this activity will occur in an increasingly empty universe as the larger-scale structure of the cosmos fades from view. If dark energy is not a cosmological constant, but instead varies over time, its impact might be more complex and could lead to different future scenarios. For instance, if dark energy's density increases over time, it could result in a big rip, where the expansion accelerates to the point that it tears apart galaxies, stars, planets, and eventually atoms. On the other hand, if dark energy's influence diminishes or changes sign, the universe might experience a deceleration or even a contraction, leading to a different form of cosmic evolution. The continued influence of dark energy on the expansion of the universe fundamentally affects our understanding of cosmological timescales and structures. For instance, the accelerated expansion suppresses the formation of new large-scale structures like galaxy clusters, as regions of space are pulled apart faster than gravity can bring matter together. This changes the rate at which the universe evolves and affects the distribution of matter. In conclusion, dark energy will continue to drive the accelerated expansion of the universe, causing distant galaxies to drift further apart at increasing speeds and leading to a future where large-scale cosmic structures become increasingly isolated. While local gravitationally bound systems may remain intact, they will exist in a vastly emptier and darker cosmos. Current and future observations, along with theoretical advancements, aim to unravel the true nature of dark energy, deepening our understanding of the universe's ultimate fate and the forces that shape its evolution. The evolution of the universe is a journey spanning countless epochs and transformations, each defined by different physical phenomena and cosmic structures. Initially, in the moments following the Big Bang approximately 13.8 billion years ago, the universe underwent rapid inflation. During these early stages, it was a hot, dense plasma of elementary particles. As the universe expanded and cooled, particles combined to form protons and neutrons, leading to the synthesis of the first simple atomic nuclei during a period known as nucleosynthesis. This era paved the way for the formation of neutral atoms and the release of the cosmic microwave background radiation when the universe cooled further, about 380,000 years after the Big Bang. The next significant phase is the stelliferous era, characterized by the formation of stars and galaxies. Gravity pulled matter together to form the first stars around 100 million years after the Big Bang. These stars forged heavier elements in their cores through nuclear fusion, and their lives and deaths, particularly through supernovae, seeded the cosmos with the building blocks for planets and life. We currently reside in this stelliferous era. However, as stars deplete their nuclear fuel, the universe will transition into the degenerate era. In this future epoch, which will occur trillions of years from now, stellar remnants like white dwarfs, neutron stars, and black holes will dominate the cosmic landscape. Over unimaginably long timescales, these remnants will also decay or merge, leading into the black hole era. In this final stage, black holes will represent the last bastions of mass before even they evaporate through Hawking radiation, signaling an end to any remaining complex structures in a universe transitioning towards an ultimate state of entropy. Black holes, those enigmatic regions of spacetime where gravity reigns supreme, undergo fascinating and complex evolutionary processes over trillions of years. Initially, black holes form from the cataclysmic collapse of massive stars or via collisions and mergers of dense stellar remnants like neutron stars. Once formed, they continue to grow by accreting mass from their surroundings, including gas, dust, and even other astronomical objects. This growth phase can last for billions of years, significantly increasing the black hole's mass and, consequently, its gravitational grip on the surrounding cosmos. Over the course of trillions of years, the universe continues to expand, indeed accelerating due to its dark energy component. As the cosmos stretches out, black holes find themselves increasingly isolated, with fewer astrophysical objects within their grasp. Eventually, they enter a phase where their external sources of mass are essentially exhausted. This is when a particularly intriguing process known as Hawking radiation takes center stage. According to the theories proposed by physicist Stephen Hawking, black holes are not completely black, but rather emit tiny amounts of radiation due to quantum mechanical effects near their event horizons. This phenomenon causes black holes to lose mass very slowly over astronomical timescales. As the cosmic environment becomes increasingly sparse, the already minuscule emission of Hawking radiation becomes the dominant factor in the black hole's evolution. This slow leakage continues for what might be called absurdly long timescales, on the order of 10 to the power of 100 years. Eventually, even the most massive black holes will evaporate entirely, leaving behind a universe deprived of its once mighty gravitational giants. Thus, black holes, which began as voracious consumers of matter and energy, end their existence with a whimper, contributing to the gradual and inexorable fade into the ultimate heat death of the universe. As we peer into the distant future of the universe, the fate of galactic remnants unfolds in a sequence of extraordinary yet subtle cosmic transformations. In the coming trillions of years, stars within galaxies will continue to burn through their nuclear fuel, culminating in a variety of end states. Massive stars will go supernova, leaving behind neutron stars or black holes, while less massive stars will cast off their outer layers to form white dwarfs surrounded by luminous planetary nebulae. Eventually, these white dwarfs will also cool and fade into cold, dark remnants known as black dwarfs. Galactic interactions and collisions, which are common in the universe's earlier epochs, will become rare as the cosmos expands. In place of these dynamic events, galaxies will slowly deplete their interstellar gas reservoirs, thus quenching future star formation. This leads to an era dominated by stellar remnants and never-to-be-revived galactic structures. The once vibrant galaxies will become stagnant collections of dead stars, stellar remnants, and diffuse dark matter, bound together by gravity, yet gradually losing cohesion over billions of additional years. Simultaneously, the influence of gravitational interactions at smaller scales will cause stars and remnants within galaxies to gravitationally scatter, a process that will accelerate when galaxies are no longer forming new stars. Over incomprehensible timescales, surviving stars will either be flung into intergalactic space or drawn into dense central regions, potentially falling into supermassive black holes. These effects, along with the slow chipping away of galactic components through gravitational radiation, will increasingly erode the structure of galaxies. In an even more far-fetched future dubbed the degenerate era, gravitational encounters and dynamical friction will harden binary stellar remnants to the point of mutual annihilation in stellar mass black holes or cause them to escape their gravitational confines. What remains of galaxies will be sparse clouds of dark, cold stellar remnants and matter spread thinly across a vastly empty and dark universe. Thus, the ultimate destiny of galactic remnants is to fade into obscurity, becoming diffuse wisps of what were once majestic, luminous islands in the cosmic ocean. Quantum phenomena, despite their roots in the subatomic realm, intriguingly influence the large-scale structure of the universe. One of the most profound examples is the role of quantum fluctuations in the early universe. During the epoch of cosmic inflation, a period of extremely rapid expansion occurring fractions of a second after the Big Bang, minute quantum fluctuations were stretched to macroscopic scales. These primordial fluctuations seeded the anisotropies we observe today in the cosmic microwave background radiation. Over billions of years, these tiny variations in density evolved under the influence of gravity, eventually leading to the formation of galaxies, clusters of galaxies, and the vast cosmic web that intertwines the universe. Another vital quantum phenomenon with large-scale implications is the concept of dark energy, which is thought to be driving the accelerated expansion of the universe. While the exact nature of dark energy remains one of the greatest mysteries in cosmology, some theories propose that it could be linked to quantum fields, possibly akin to the so-called vacuum energy or a quintessence field. At this juncture, quantum mechanics suggests that even empty space has a baseline energy level, and it's hypothesized that this energy is what fuels the universe's accelerating expansion. As space stretches, this dark energy exerts a repulsive force, overpowering gravitational forces on large scales, thereby pushing galaxies apart at an ever-increasing rate. Furthermore, potential quantum modifications to general relativity, commonly referred to as quantum gravity, could also play a significant role in shaping our cosmological understanding. In the quest to unify quantum mechanics and general relativity, various theories such as string theory and loop quantum gravity propose that spacetime itself may have a discrete or quantized structure at extremely small scales. While these effects are negligible at everyday scales, they could have significant consequences for the universe's dynamics at both the smallest and largest scales. For example, during black hole formation and evaporation, quantum gravitational effects might influence the black hole's ultimate fate, as well as the dispersal of information back into the universe, addressing the so-called information paradox. In sum, quantum phenomena, though originating in the minute realms beyond human perception, weave a complex tapestry that profoundly affects the vast and ever-expanding universe. These interactions paint a picture where the very small scales inform and shape the vast cosmic structures we observe, outlining the intricate and beautiful interplay between the laws governing the subatomic and the grand expanse of the cosmos. The long-term fate of the universe is a question that intertwines the principles of cosmology, astrophysics, and theoretical physics, requiring a deep understanding of both observational data and the laws of physics. Scientists rely on a combination of empirical evidence and theoretical frameworks to predict how the cosmos will evolve over incredibly long timescales. One of the primary tools in predicting the universe's fate is the study of its current rate of expansion. Since the late 20th century, astronomers have observed that the universe is not merely expanding, but its expansion is accelerating. This discovery was made through observations of distant type Ia supernovae, which act as standard candles, objects with known luminosity. By measuring their apparent brightness, scientists can determine their distance and subsequently track how the universe's expansion rate has changed over time. This accelerated expansion is attributed to dark energy, a mysterious force that makes up about 70% of the universe's total energy content. The nature of dark energy remains one of the biggest questions in physics, but its properties are crucial for predicting the universe's ultimate destiny. In addition to observing cosmic expansion, scientists also build detailed models based on the current understanding of physical laws. These models incorporate the behavior of dark energy, dark matter, and ordinary matter, using equations derived from general relativity and quantum mechanics. Different scenarios emerge from these models, shaping potential fates for the universe. If dark energy continues to drive accelerated expansion indefinitely, the universe could end in a big freeze, where galaxies drift apart, stars burn out, and the cosmos becomes an increasingly cold and dark place. Alternatively, if dark energy were to change in nature, it could lead to a big rip, wherein the expansion eventually becomes so intense that it tears apart galaxies, stars, and eventually atomic nuclei. Another important aspect of predicting the universe's fate is understanding the role of black holes and quantum phenomena. Over extraordinarily long timescales, stellar remnants like white dwarfs and neutron stars will either merge into black holes or be ejected from galaxies. These black holes will slowly evaporate through a process known as Hawking radiation, predicted by quantum theory, losing mass until they vanish completely. This contributes to a vision of the universe transitioning into a state dominated by diffuse low-energy particles, leading to what's termed the heat death, or big chill, where entropy reaches its maximum and no thermodynamic work is possible. In essence, predicting the long-term fate of the universe is an exercise in extrapolating current knowledge and exploring the boundaries of fundamental physics. It combines precise astronomical observations, sophisticated theoretical models, and a deep commitment to understanding the fundamental forces shaping the cosmos. Through this tapestry of science, researchers strive to glimpse the distant future of our universe, unraveling the profound cosmic story that continues to unfold on a scale both vast and minute. The concept of the multiverse, where our universe is but one of many possibly infinite universes, brings profound and intricate implications for both the future and the very nature of our universe. Multiverse theories emerge from various branches of physics, such as cosmology, quantum mechanics, and string theory, each proposing different forms of multiverses with diverse characteristics and consequences. One of the central implications of multiverse theories is the potential diversity in the physical laws and constants across different universes. In some scenarios, such as the bubble universe model of eternal inflation, our universe might be one of countless bubbles within an ever-expanding cosmic landscape. Each bubble could have different values for fundamental physical constants, like the gravitational constant or the cosmological constant, resulting in universes with vastly different properties. This might offer an explanation for the fine-tuning observed in our universe, where conditions are just right for the existence of stars, planets, and life, as one of numerous possible configurations where life-supporting conditions happen to arise. From a viewpoint focusing on the future, these multiverse theories could also suggest scenarios for our universe's end. For example, some multiverse models involve phases of cosmic evolution where universes can birth new universes through mechanisms like black hole formation or quantum fluctuations. These child universes would lead independent existences, potentially with different physical laws, but related through a shared ancestry. Thus, even as our universe meets its ultimate fate, whether it be a big freeze, big rip, or heat death, the multiverse continues to thrive, with new universes perpetually emerging from the cosmic substrate. In quantum mechanics, the many worlds interpretation offers another perspective, proposing that every quantum event spawns a branching of the universe into parallel realities where every possible outcome of that event occurs. This interpretation implies that every possible future is realized in some version of the universe, leading to an almost unimaginably rich tapestry of parallel existences. Although it doesn't change the observable fate of our tangible universe, it broadens the context in which our universe's future plays out, embedding our cosmic history within an infinite array of alternate timelines. Furthermore, multiverse theories challenge our understanding of concepts like entropy and the arrow of time. In a multiverse, where new universes can constantly emerge and old ones evolve, the very idea of a singular, all-encompassing heat death might not apply. Instead, entropy and time might function differently across various regions of the multiverse, leading to a complex, interconnected landscape where the end of one universe is merely a part of a larger cosmic dynamism. Ultimately, multiverse theories underscore the profound scale and mystery that surrounds our universe. By suggesting that our cosmos is part of an immense, potentially infinite collection of universes, these theories expand our philosophical and scientific horizons, inviting us to ponder not just the fate of a single universe, but the perpetual dance of creation and dissolution on a grand, multiversal stage. Whether we can ever empirically verify these theories remains a colossal challenge, but their implications continue to stimulate thought and inspire further exploration into the deepest questions of existence.